Hey guys, today we're going to be going through Chapter 10 for your Math 200 class. So this chapter is all about hypothesis testing regarding a parameter. So last week we worked with confidence intervals, which is one kind of type of inference that we do to take our sample data and put it back on our population. Hypothesis testing is the other big one that we do. So we're going to start with section 10.1, which just goes through kind of the language of hypothesis testing, how we set up hypothesis tests, that sort of thing. And then we're going to go ahead and conduct hypothesis tests for proportions and for means. So a couple of definitions first. So a hypothesis is just a statement regarding a characteristic of one or more populations. In this chapter, we're going to look at hypotheses regarding a single population parameter. Chapter 11, we'll look at two at once. But hypothesis testing is just a procedure based on sample evidence and probabilities that is used to test statements regarding a characteristic of one or more populations. So basically what we do is we take our sample data and we use probabilities to determine whether our hypothesis could be true or not. So let's look at a couple of examples here. We're going to revisit these a couple of times, but these are just examples of claims regarding a characteristic of a single population. So for example, in 2008, 62% of American adults regularly volunteered their time for charity work, and a researcher believes that this percentage is different today. So this might be the hypothesis that they're testing. Or we could look at something like this, where according to a study published in March of 2006, the mean length of a phone call on a cell phone was 3.25 minutes. But a researcher believes that the mean length of a call has increased since then, so we could be testing that. Or we could look at this example here. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes that that standard deviation has decreased, so they would like to test that. Now, we're not going to actually do any hypothesis testing with standard deviations, but we will do one similar to the first two claims where we have a proportion and a mean. So one kind of cautionary note here, we test these types of statements using sample data because it's typically impossible or very impractical to actually gain access to an entire population. But if population data is available, then we don't really have a need for inferential statistics. So if you're only interested in a small population, like one particular class or something like that, you can just use the entire population data. But typically we do not have access to that, so that's why we use sample data in order to infer back on our population. So steps in hypothesis testing include the following three things. The very first thing we need to do is we need to make a statement regarding the nature of the population. And then we need to go ahead and collect evidence, which is going to be our sample data, in order to test that statement. So we create our hypothesis, we collect data, and then the third thing that we do is we analyze that data to assess the plausibility of the statement. So we decide if we should reject or fail to reject our null hypothesis given our sample data. So I mentioned null and I didn't mention alternative yet, but the null hypothesis, it's typically denoted H naught. We read this H naught, it's really an H with a little zero there. It's a statement to be tested. So the null hypothesis is a statement of no change, no effect, no difference. And basically it's just assumed to be true until evidence indicates otherwise. Now the alternative hypothesis, denoted H1, or you might see denoted HA for H alternative, is a statement that we're trying to find evidence to support. So we believe that a proportion has increased or decreased or just that it's changed, and we're trying to figure out if there's evidence to support that. So that would be our alternative hypothesis. So there are three main ways to set up the null and the alternative hypotheses, and these aren't too tricky once you get used to the wording that you'll see. Typically, you're going to see keywords like increased, decreased, or changed, and that's going to help you figure out how to set up your null and your alternative hypotheses. So the first example here is just an equal versus a not equal hypothesis. This is called a two-tailed test because really all we're trying to figure out is whether the parameter is different than some value. So the null hypotheses in each of these scenarios are all the same. That the parameter, which is either a population mean or population standard deviation, or sorry, not standard deviation, proportion, is equal to some value. Okay, so those are all the same. H naught is parameter equals some value. Now, the alternative hypothesis is the one that changes. So for the two-tailed test, the alternative hypothesis is that the parameter is not equal to some value. So we don't necessarily know if it's increased or decreased. We just are thinking that it's different, okay? Now in the second scenario, we have a left-tailed test. That's when we have less than. So in this case, our alternative hypothesis is that the parameter is less than some value, so that it's decreased over time, or with whatever respect we're talking about. So that would be kind of a decrease would be a good kind of keyword. It's fallen, something like that. The third basic way to set up the null and the alternative hypothesis is to have your null hypothesis the same, alternative is greater than, so something has increased over time, or it's larger than it was before, okay? So this would be that the parameter is greater than some value, and this is going to be a right-tailed test. Now these, you'll get pretty used to setting these up, but another kind of way to think about the null hypothesis is that it's a statement of basically status quo, no difference. It always contains a statement of equality. You're always going to have parameter equals value. So the null hypothesis is assumed to be true until we have evidence to the contrary. And we seek evidence that supports the statement in the alternative hypothesis, and that's done using our sample data. So let's look at the examples that we talked about before, and let's see if we can set up some hypotheses for these. So for A, we have in 2008, 62% of American adults regularly volunteered their time for charity work, and a researcher believes that this percentage is different today. So the key word here is different. The researcher doesn't have an inclination as to whether that proportion has increased or decreased. They just think that it's different. So in this case, we actually have a two-tailed test where our null hypothesis is that p is equal to 0.62. That's our statement of no change. And this one we have a population proportion because we're talking about the percentage of American adults who regularly volunteer their time. We have a percentage here. And our alternative hypothesis is going to be that the percentage is different, so p not equal to 0.62. Again, the researcher doesn't indicate whether he thinks that the proportion has increased or decreased, just that it's different. So this is going to be a two-tailed test. Let's look at B here. So according to a study published in March of 2006, the mean length of a phone call on a cell phone was 3.25 minutes, and a researcher believes that the mean length of a call has increased since then. So increased is your keyword. In this case, we're talking about a mean because it's talking about average length of a cell phone call. So it's going to be around our population mean mu. So if the mean is no different than it was in 2006, it's just going to be 3.25 minutes. So our null hypothesis is just that mu equals 3.25. Now it says that the researcher believes that the mean call length has increased. So he thinks that it's higher. So our alternative hypothesis is going to be that mu is greater than 3.25. Now if you remember greater than, that is called a right-tailed test. And finally, let's take a look at this manufacturing example. Standard deviation of amount of wine put in a bottle was 0.23 ounces. New equipment, so the quality control manager thinks that the standard deviation has decreased. So since we're dealing with a population standard deviation, it's going to be testing around sigma. And again, this is not something specifically that we're going to do in this course, but the general idea in terms of setting up the null hypothesis is something you should still be comfortable with. So if the standard deviation with the new equipment hasn't actually changed, it's still going to be the 0.23 ounces. So our null hypothesis is just that sigma equals 0.23. Now, since they have new equipment, the quality control manager thinks that the equipment is more standardized, so the standard deviation is going to decrease. So our alternative hypothesis is going to be that sigma is less than 0.23. And if you recall from a few slides back, this is called a left-tailed test. Okay, now if you think about the possible outcomes from a hypothesis test, we have four basic things that can happen. So we can decide to reject the null hypothesis when the alternative hypothesis is true. And that would be a correct decision. So we should reject our null hypothesis if the alternative is actually true. So that's a correct decision. We could also fail to reject the null hypothesis when the null hypothesis is true. That's also a correct decision. And then there are two kind of errors that we can make. So the first error, it's called a type 1 error, is when we reject the null hypothesis when the null hypothesis is actually true. So meaning that the null hypothesis is true, but based on our sample evidence, we decide to reject it. So that's an incorrect decision. So that's a type 1 error. There's also something called a type 2 error, which is the other kind of incorrect decision that you can make. And that's when you fail to reject the null hypothesis when the alternative is actually true. So in that case, the alternative hypothesis is the true one, but you fail to reject the null hypothesis. So your decision, again, is incorrect, and that's a type 2 error. So let's look at the same example. 62% of American adults regularly volunteered their time for charity work in 2008. A researcher believes that this percentage is different today. So we want to talk about what it would mean to actually make a type 1 or a type 2 error in this scenario. So if we scroll back for just a second, recall that a type 1 error means that we reject H0 when H0 is true. So in this case, a type 1 error would mean that we would reject H0, meaning that we would conclude that the proportion is not equal to 0.62, when actually the true proportion of Americans 18 years or older who participated in some form of charity is currently 62%. So we rejected H0 when H0 was actually true. And a type 2 error is just the opposite. The sample evidence leads us to believe that the current percentage of Americans 18 and older who did participate in some form of charity work is indeed 62%, when actually the percentage is different than the 62. Now we have a couple of definitions in terms of the errors that we can make. Alpha you've seen before, and that's their probability of having a type 1 error. Or you could think of it as the probability of rejecting H0 when H0 is true. Now beta, this is the new one, this is the probability of a type 2 error. And this is the probability of failing to reject H0 when H1, or the alternative, is true. So the probability of making a type 1 error, alpha, should always be chosen by the researcher before any data is actually collected. And this is also referred to as your level of significance, which we dealt with when we were doing confidence intervals in the last chapter. And that's just your probability of making a type 1 error. Now, the important thing to keep in mind with these errors is that we want to minimize them, but as the probability of a type 1 error increases, the probability of a type 2 error decreases, and vice versa. So they have kind of an inverse relationship here. So if we decide to have a smaller value for our alpha, we're going to have a larger beta, and vice versa. Now, one kind of cautionary note here is that we never actually accept the null hypothesis, because without having access to an entire population, we don't know the exact value of the parameter stated in the null. Just kind of like the same way that our court system works, we never declare a defendant innocent, but rather we say that he's not guilty. So we just do not reject the null hypothesis. Or sorry, we say that we do not reject the null hypothesis instead of saying that we accept, all right? So we fail to reject. So let's take a look at section 10.2, which actually gets into hypothesis testing for a population proportion. And then in the next section, we're going to take a look at population means. So a couple of things to recall from previous chapters. We know that the best point estimate of P, the proportion of the population with a certain characteristic, is going to be given by P hat, which is found by taking x over n, where x is the number of individuals that have the characteristic that you're talking about, and n is the sample size. Now, we also know that the sampling distribution of P hat is approximately normal, with mu of p hat equal to p and the standard error equal to the square root of p times 1 minus p over n, provided that a couple of things are true. Simple random sample, n times p times 1 minus p has to at least be 10, and the sampled values are independent of one another. So in order to test hypotheses regarding a population proportion, we have to have these same three things happen. The sample is obtained using simple random sampling, n times p naught times 1 minus p naught is greater than or equal to 10, and the sampled values are independent of each other. So the very first step, before we actually look at any numbers, we're going to go through all of the steps, and then we'll go through all of the steps again in the context of a problem. And I will also show you how to do this using StatCrunch. So step 1 is to determine the null and alternative hypotheses. And again, they can be structured in one of three ways. Now you'll notice the only difference between these is that we have p's instead of just the word parameter, because we're talking about a population proportion. So the null hypothesis is the same for all of our tests, which is that p is equal to p naught, and p naught is going to be some value. It's just the assumed value of the population proportion. So it's whatever we believe to be true. Now, our alternative hypothesis depends on which type of test we have. So if we have a two-tailed test, we have p not equal to p naught. If we have a left-tailed test, we have p less than p naught. So this would be something where we think a proportion has decreased, or we could think that a proportion has increased, which would be a right-tailed test, where p is greater than p naught. Step 2 is to select a level of significance, alpha, based on the seriousness of making a type 1 error. Now typically in this particular course, your alpha value is going to be given. If it's not, choosing 0.05 is kind of a nice benchmark to use, but it's important to talk about what a type 1 versus a type 2 error actually means in the context of a question, so that you can decide which one is worse in the given scenario. So step 3 we can do either by hand or in StatCrunch. If you're going to do it by hand, the test statistic looks like this. It's a z statistic since we're talking about a proportion, and it's found just by taking p hat minus p naught divided by the square root of p naught times 1 minus p naught over n. And then we just use table 5, our normal table, to estimate the p-value. Now it's important to note that if you have a two-tailed test, you have both sides, okay? So if you have not equal to, you need to take whatever value you get from looking it up on the table, and you need to multiply by 2, okay? Now the left-tailed test is the area to the left. So you're just going to go to your table, look up your value. Right-tailed is the area to the right. So once you have your test statistic, you have to think back to when we did z-scores, and you'll have to do 1 minus that value. Now, the one thing to note here with your two-tailed test, if you have a value where, let's say that your original z value is somewhere over here, when you look it up on your table, the table is automatically going to give you everything to the left. So in order to find your p-value, first you would have to do 1 minus the table value, and then multiply by 2. You always want to make sure that your p-value, since it's a probability, is somewhere between 0 and 1. If you get a value that's not between 0 and 1, it means that you did not take the correct steps. So StatCrunch can be used for these steps as well, and in order to do that, we go to Stats, Proportion Stats, one sample with summary or with data depending on how it's provided. Typically it's going to be with summary. And then step 5 is to actually make a conclusion. So if your p-value is less than alpha, then we decide to reject the null hypothesis. And then we state the conclusion in a full sentence for step 6. But the whole idea is that the probability is, or the p-value is the probability of obtaining a sample that is as rare or more rare than what you got for your sample under the null hypothesis. So meaning that if the null hypothesis is actually true, what's the likelihood that we would get a result that we did? Now, if the p-value is less than your alpha, then you're going to go ahead and reject the null hypothesis. This gives you kind of motivation to say that yes, probably our null hypothesis is not true. But if your p-value is larger than alpha, then we fail to reject our null hypothesis. So let's take a look at an example that has actual numbers in it. So in 1997, 46% of Americans said that they did not trust the media when it comes to reporting the news fully, accurately, and fairly. And then in 2007, a poll of 1,010 adults nationwide, 525 of the 1,010 stated that they did not trust the media either. So at the 0.05 level of significance, we want to determine if there's evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. So lots of information here, but the important thing is to go ahead and pull out against, that's our 0.46. And then you'll see that we have sample data for 2007. We have a total of 1,010 as our sample size, that's our N. And our X, that's the people who said that they did not trust the media, is 525. And our alpha is 0.05. And then the other keyword is increased. So we think that it has increased. So we want to know if P is greater than 0.46. Very first thing we're going to do, though, is verify that the requirements have been met. So it's a simple random sample, so that's fine. And n times p naught times 1 minus p naught, if we do this, we have 1,010 times 0.46. Again, this is from our null hypothesis. Times 1 minus 0.46 is 250.8, which is greater than 10, so that's good. And the sample size, 1,010 is a pretty small sample size. We're interested in, I think it said all adults. So this is definitely less than 5% of your population size. So the assumption of independence is also met. So if we set up our null and our alternative hypotheses, we have the null hypothesis set up this way, where we have p equals 0.46. So this was back from 1997. This is kind of what we believe to be true. Now, based on what the researcher thinks, he is under the impression that the proportion has increased. So the alternative hypothesis is that p is greater than 0.46. Step 2 is to just go ahead and state the level of significance, which is just 0.05. Step 3 would be to find the sample proportion and the test statistics. So the sample proportion is found by taking the people who kind of answered that they did not really trust the media, which was the 525, out of the 1,010, and we get a sample proportion of 0.52. So the test statistic is found using this formula right here. That was from a few slides back. And if we actually do this, we have 0.52, which is our p hat, minus our p naught, which is from our null hypothesis, divided by the square root of p naught times 1 minus p naught over n. And if we do this very carefully in our calculator, you're going to get 3.83 as your test statistic. Now, this is a right-tailed test. So the p-value is going to be the area under the standard normal distribution to the right of 3.83. So I'm going to go ahead and pull up the normal table here. So let me minimize this. And here is my formula, or my tables. And here's my standard normal table. So 3.83, if you start to look for this on there, you're going to see 3.4 is the very largest value that you have. So 3.83 is essentially just off of our table. The probability of getting something to the right of 3.83 in terms of a z-score is going to be very, very close to 0. So it's very, very unlikely. So we can also kind of verify that this is the case using StatCrunch. So I'm going to show you guys how to do this now. So I have, let's see, let me get rid of this part. We have a little more room. So let me pull up StatCrunch. So I put kind of a little recall down here, which just has the information from our problem. And in this case, I'm doing stats, proportion stats, because I'm talking about a proportion. And I'm going to have to scoot this over a little more. Proportion stats. I just have one sample. And in this case, my data is summarized. So I have with summary here. And I put my number of successes. So I had 525 out of 1,010 people say that they did not trust the media. And I want to run a hypothesis test. The proportion that I believe from my previous estimate was the 0.46, but I think it's increased. So under this, instead of having it as a two-tailed test, I need a right-tailed test, which is just going to be this greater than. You don't have to do anything with the confidence interval. This is what we did in the last chapter. But right now we're doing a hypothesis test. So this is selected right here. And then I do compute. and it gives me all the information that I need here. So it gave me the sample proportion. I had 0.52, that was my 525 over 1010. This is a more exact value here. It has my standard error there, has my z statistic, the 3.81, which was from the previous slide. This might be a little bit different because we rounded our 0.52. This one is not rounded. And then our p-value, they agree, is very, very small. You see that it has this less than symbol, so it's less than 0.0001. So very, very small our p-value is. So at this point, we have kind of conclusions that agree using StatCrunch and using the by hand method. So we can make a conclusion. So since our p-value is very, very small, it's less than alpha, we're going to go ahead and reject the null hypothesis. So we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the percentage of Americans that do not trust the media to report fully and accurately has in fact increased since 1997. So that means that our sample data did kind of support this. The researchers' idea that the percentage of Americans that don't trust the media has actually increased. All right, now let's take a look at section 10.3, which talks about hypothesis testing for a population mean. So a couple of definitions. This is a reminder of students' t-distribution from the previous chapter. But in order to test hypotheses regarding the population mean, assuming the population standard deviation is unknown, which typically it is, we're going to use the t-distribution instead of z. And we talked about why in the last video. But when we replace sigma with s, we have this test statistic here, x bar minus mu divided by s over the square root of n, which follows a student's t-distribution with n minus 1 degrees of freedom. Now, in order to test hypotheses regarding the population mean, we can use the following steps provided that a couple of things are true. The sample is obtained using simple random sampling, there aren't any outliers, and the population is from the population from which the sample is drawn is either normally distributed or has a large enough sample size, approximately 30 or higher. And the sampled values have to be independent of each other. So your sample size cannot be more than 5% of your population size. So the steps are going to look very similar to the steps from the previous hypothesis test. In this case, your null and your alternative hypotheses look absolutely identical, except instead of having p for a proportion, we have mu for a mean. So again, we have a two-tailed test, a left-tailed test, and a right-tailed test. And mu naught is going to be the assumed value of the population mean. The second step is to just select a level of significance alpha based on the seriousness of making a type 1 error. This is the same as it was before. Step 3 is to compute the test statistic, which is not too bad looking at all. Basically, you just take x bar minus mu naught, which is from your null hypothesis, and you divide by the s over the square root of n, and that's going to follow students' t-distribution with n minus 1 degrees of freedom. And then we have to use table 6 to approximate the p-value. So if you have a left-tailed test, you're finding the area to the left. If you have a right-tailed test, you're finding the area to the right. And if you have a two-tailed test, you're taking 2 times that value so that you get values in both tails. We can also use StatCrunch to perform those steps, which is going to be under stats t-stats, which is the same thing that it was before. And then one sample with summary. And then instead of a confidence interval like we did in chapter 9, we're going to select the hypothesis test. And our conclusions are going to be exactly the same. So if our p-value is less than alpha, we reject the null hypothesis. Basically, that means that our sample provided enough evidence that we can reject our null hypothesis. And then we go ahead and we state the conclusion. Now, one kind of important thing to note is that the procedure is robust, which means that minor departures from normality are not going to adversely affect the results of the test. But if we have small samples and we have outliers, we should not use this procedure. So let's look at this example here. Let's assume the resting metabolic rate, or RMR, of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their mean RMR to be 5,708.07 with a standard deviation of 992.05. And we want to test at the 0.05 level of significance whether or not there's any evidence to conclude that the mean RMR of males who are listening to calm classical music is any different than 5,710 kilojoules per day. So we're going to assume that the RMR of healthy males is 5,710. Now we know we're going to have a two-tailed test because it just said the word different. It didn't say increased or decreased. So this is a two-tailed test. Now our null hypothesis is going to be that mu is equal to 5,710. And our alternative is going to be that mu is not equal to 5,710. We know that alpha equals 0.05, and we know that the sample mean, x bar, is 5,708.07, and the sample standard deviation is 992.05. So in order to compute our test statistic, we use this formula here. So we have our x bar, which is our sample mean, minus our mu naught, which is from our null hypothesis, and that's divided by s over the square root of n. In this case, we had 45 males in our sample. And make sure if you're doing this in your calculator all at once, you have parentheses around the numerator, parentheses around the denominator, and you should get a value of negative 0.013. Now, since this is a two-tailed test, we need to look at the t-distribution. And I'm going to go ahead and minimize this here so we can go ahead and pull that up and I can show you. Because this is a little different than our normal distribution in terms of looking up the values. So t-distribution is table 6. First thing that we want to identify is the number of degrees of freedom. So in this case, we have a sample size of 45, so we have 44 degrees of freedom. So I'm going to scroll my way down there. Now you'll notice I don't have 44 on here. What you can do is you can just use the closest. I'm just going to use the 40. You'll notice that the values between 40 and 50, these are very, very close. So our answer is not going to differ depending on which we use. So I'm going to look at 40 here. Now I know that the critical value is negative 0.013. Now one thing you should notice is that in the body of the t-distribution, we only have positive values. So when we're looking for a critical value, we're looking for the absolute value of that critical value in the table. Now, what we're doing, because we don't know our probability, is basically we're looking in the body of the table in order to try to find the corresponding probability up at the top. So if I look at 44 degrees of freedom, or 40 degrees of freedom, and I look for 0.013 in my table, what you'll notice is that this is increasing as we go in this direction. So 0.013 is off the table somewhere to the left. So we know that our p-value, or the corresponding probability when I look it up in the table, is something larger than 0.25. I'm not sure what exactly it is, but it's definitely larger than 0.25. Now, if you think about it, we have a two-tailed test because I just wanted to test if the RMR was different, not necessarily less than or greater than. So in this case, when you have a two-tailed test, you have to find your p-value by taking 2 times the table percentage. So in this case, I take 2 times 0.25 and I get 0.5. Now I know that my p-value is at least 0.5. It's going to be quite a bit larger than that because if you look for 0.013 on my table, you'll notice 0.681 is the very smallest value I have. So it's kind of way off of my table. So now if I go back, let me minimize this again. We're going to use StatCrunch now, so we can get an actual p-value using this. So let me navigate back to StatCrunch, and this time I'm going to use t-stats because I have a t-statistic since I have a mean, and I have just one sample, and this time I have with summary as well. Now my sample mean, if we recall, was 5,708.07. Sample standard deviation was 992.05, and I had a sample size of 45 males. Now I wanted to test the mean being 5710, and this time I want the not equal to. So I just click compute, and you'll see that this gives me the same t-stat, negative 0.013. This one gives me an accurate p-value, 0.9896. So we knew that it was at least 0.5 just by using our table, but this is an accurate p-value of 0.9896, which is going to be greater than alpha. So we're going to fail to reject the null hypothesis. This means that our sample data did not provide any evidence that suggests that we should reject our null hypothesis. So there was insufficient or not sufficient evidence at the 0.05 level of significance to conclude that the mean RMR of males listening to calm classical music differs in any way from 5,710 kilojoules per day. Okay, one last topic in this chapter is the difference between practical and statistical significance. So when large sample sizes are used in hypothesis tests, the results often end up being statistically significant, even though the differences are not really practically significant. So if you think about practical significance, this just refers to the idea that even though small differences might exist between a statistic and a parameter, the difference might not be large enough to cause any concern or be considered important in some way. So the easiest way to kind of look at this in further detail is to look at an example. So in 2003, the average age of a mother at the time of her first childbirth was 25.2 years. We want to determine if the average age has increased. So we take a random sample of 1,200 mothers, which is a pretty large sample, and it's found to have a sample mean of 25.5 years with a standard deviation of 4.8 years. And we want to determine whether this is increased. So our null hypothesis is going to be that mu equals 25.2, and our alternative is a right-tailed test that it's increased 25.2, or increased from 25.2. Alpha is 0.05. Our sample mean is 25.5, so our test statistic is calculated by taking our 25.5 minus our null hypothesis 25.2 divided by 4.8, which is our sample standard deviation, over the square root of 1200, which in this case gives us a test statistic of 2.17. So if I go to my table and let's see, scoot over my table, I have a normal distribution this time. So oh wait, hold on, what are we doing here? Oh, we're talking about mean. So we have 2.17, this is a t-value, sorry. So I'm on my t-distribution table. This one, let's see, I have 1,199 degrees of freedom. All right, closest value is going to be 1,000, so I'm just going to use that. And I'm looking for 2.17 on my table. So if you look in the body of your table, 2.17, you're not going to find the exact values, but what you'll notice is that you find two bounds, okay? So 2.17 is directly between 2.056 and 2.330. So this means that my p-value is within these bounds as well. So my p-value is somewhere between 0.02 and 0.01. Now I don't know exactly what it is, but it's somewhere between those two values. And that would mean that our p-value is less than alpha, so we would go ahead and we would decide to reject our null hypothesis. So we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the mean age of a mother at the time of her first childbirth is greater than 25.2. Now, if you think about this conclusion, yes, it's statistically significant because we conducted a test and it indicated that that was the case. But if you think about it, the difference between 25.2 years old and 25.5 years old really has no practical meaning. So in this case, although there is statistical significance, there isn't really any practical significance. So kind of cautionary note here is that large sample sizes can often lead to statistically significant results when the difference between the statistic and the parameter isn't enough to be considered practically significant. Now, this is often done in like medical studies where ones maybe that aren't published in journals necessarily, but like where a company is trying to sell like a weight loss drug or something like that. they'll take a really large sample size so that even a very small average weight loss results in something that is statistically significant, so that they can say that there's significance. But if you think about it, if the average weight loss is only 0.3 pounds, that doesn't practically mean anything. Okay, so losing 0.3 pounds really doesn't make a difference at all in terms of physical appearance or anything like that. Your weight would fluctuate by that amount just throughout the day. So it's important to kind of be wary of any statistical studies where it seems like the actual mean that they're testing against and the mean that they had from the sample are not very different, because even if something is statistically significant, it doesn't mean that it has practical significance. All right, the last thing is section 10.4, which is really just a nice chart which kind of goes through what to use when. So we have 3 different things. We are not dealing with the green over here, our standard deviation and our variance. So we're going to just focus on proportion and mean. So if you have a proportion, a couple of things have to be true, but as long as those are true, you calculate a z-statistic, and then you find the probability and make your conclusion. If you have a mean, then a couple of things have to be true for that as well, but in this case, you take a t-statistic and you look that up on the table. And again, this is one that's a little different. You're looking across your degrees of freedom in the body of the table, and then finding the corresponding probabilities that are in bold at the top. Now, one other thing that I really want to emphasize here is finding those p-values. So I would always make sure you draw yourself a little picture with the test statistic and the shaded area, and make sure that your answer makes sense. So the important thing to not forget, which is kind of the most common thing to forget, is to forget to multiply your p-value by 2 when you're doing or multiply your probability by 2 when you have a two-tailed test. So in order to calculate your p-value for a two-tailed test, which is anything where your alternative hypothesis says that the proportion or the mean is not equal to, so using the not equal to symbol, you need to make sure that you take whatever probability you found and multiply that by 2 in order to get your p-value. That is it for chapter 10. Please let me know if you have any questions.